Module 8, Lecture A, Image and Time Data.
By the end of this lecture, you will be able to represent simple inspection images and sensor time series using NumPy arrays and pandas tables, extract beginner-friendly features from image style grids and temporal engineering signals, and compare model performance across tabular, image style, and time series feature sets. Image style arrays. Image arrays. An image can be understood as a grid of numerical measurements where each pixel stores brightness, color, or another value such as temperature. This array structure preserves spatial layout, making images easy to analyze and transform. In AI workflows, images are not just visual files. They are numerical data that can support tasks like inspection and defect detection. A grayscale inspection image can be treated as a grid of brightness values, where each value corresponds to a pixel's location. This structure helps reveal patterns that may indicate defects, such as dark lines suggesting scratches, or bright clusters suggesting overheating. By comparing unusual regions with their surroundings, we can identify where potential problems are and how intense they appear. Color images store red, green, and blue values for each pixel, allowing computers to analyze color as well as brightness. This is useful for tasks such as detecting plant stress, spotting food damage or contamination, and identifying recyclable materials by color and shape. Representing images as arrays makes these visual details easier to compare, isolate, and process systematically. Python code. Image arrays. Create a small image for inspection by storing its pixels in NumPy arrays, then describe selected image regions using simple features. The script begins by importing NumPy for numerical work with arrays and matrices, and Matplotlib's plotting tools for creating visualizations. These libraries provide the foundation for the image processing and display tasks that follow. An 8x8 image array is created with all pixels set to 180, representing a bright metal surface. A smaller rectangular region is then changed to 45 to represent a darker area. This simple setup creates contrasting regions that can be analyzed and visualized later. We first confirm that the image array is 8x8 and two-dimensional. This verifies that the data has the expected grayscale image structure before any further processing, helping catch shape or format errors early. The image is summarized using two brightness measures. First, the average pixel value gives the overall brightness as a precise floating point number. Then, pixels with brightness below 80 are counted as dark pixels. This count helps highlight possible defects or areas of interest in the image. The image is split into two sections using row slicing. The upper section includes rows from the start up to the fourth row, while the lower section includes rows from the fourth row to the end. This creates two separate arrays, making it easier to analyze and compare different parts of the image. We store the average brightness of the image's top and bottom halves in a dictionary. Each region's mean brightness is calculated, converted to a precise numeric value, and saved under a clear label. This makes it easy to access and print the two brightness values later. This output gives a quick summary of the image data. It reports the image dimensions, pixel data type, average brightness, and the number of very dark pixels that may indicate defects. It also compares the average brightness of the top and bottom halves to show how lightness varies across the image. Set up a 4x4-inch plotting canvas, then display the image array in grayscale using Matplotlib's image display function. The grayscale color map shows pixel values as shades from black to white, with the brightness range fixed from 0 to 255. The plot is labeled as a tiny grayscale inspection image to clarify what is being shown. A color bar is added to indicate brightness values, and the x-axis ticks are set from 0 to 7, so each image column can be easily identified. To make the image grid easier to read, set the y-axis tick marks to match the row indices from 0 to 7. Then label the horizontal axis as column position and the vertical axis as row position, so viewers can clearly understand how the image is organized. The tight layout function in matplotlib adjusts the plot spacing so labels, titles, and other elements fit cleanly without overlapping. The show function then displays the finished plot, making the image and its annotations visible for analysis and presentation. This script builds a small 8x8 grayscale image that represents a bright metal surface with a darker rectangular area in the center. It then summarizes the image by reporting its size, pixel type, average brightness, number of dark pixels, and the average brightness of the top and bottom halves. Finally, it displays the image with a grayscale color map and brightness color bar so the pixel values can be inspected visually. Array Shape Basics. In NumPy, a grayscale inspection image is represented as a grid of numbers, where each number gives a pixel's brightness. The array shape describes the grid's rows and columns, which correspond to the image's height and width. This shape lets the computer interpret the numbers as organized image data, rather than as unrelated values. Color images are stored with a more complex shape because each pixel includes multiple values, usually for red, green, and blue. The array must represent the image height, width, and color channels. In inspection tasks, different channels can reveal different features, such as bruising or surface defects. Understanding this structure helps prevent treating a color image as just a simple grid of numbers. When working with many images, array shape shows how the data is organized. Each image has height, width, and sometimes color channels, while a full dataset adds another dimension for the number of images. Machine learning tools need these shapes to be consistent, so images may need to be standardized before analysis. Python code array shape basics. Image arrays store inspection grids by organizing data into rows, columns, and channels. Using small arrays makes the structure easier to understand while keeping the examples simple. We begin by importing NumPy, a library for efficient numerical computing. It lets us work with arrays, which are useful for storing and processing image data in a compact form. We create a simple grayscale image as a 4x4 array, where each value represents a pixel intensity from 20 to 90. This small grid makes it easy to see how image data is structured and prepared for later manipulation. A color image is prepared by making 3 channels from the grayscale image. The red channel is slightly brightened by adding 10 to each pixel. The green channel keeps the original values, and the blue channel is slightly darkened by subtracting 10. These channels can then be stacked to form the final color image. To build a color image from separate channels, use NumPy's stack function to combine the red, green, and blue grayscale channels into one 3-dimensional array. Stacking along the third dimension makes each pixel store 3 intensity values, one for each color channel, producing a full color image. A second grayscale image is created by increasing each pixel value by 5, making it slightly brighter than the original. The original and brighter images are then combined with NumPy's stack function along a new first dimension, forming a batch of 2 images. This makes it possible to process multiple images together, which is common in machine learning workflows. We verify the expected array shapes before continuing. The grayscale image is 4x4. The color image is 4x4 with 3 color channels. And the grayscale batch contains 2 4x4 images. These checks confirm the data is organized correctly and help catch shape errors before printing summaries. This section checks the shapes of different image arrays to understand their structure. A grayscale image shape shows its rows and columns, while a color image shape also includes the number of color channels per pixel. For a batch of grayscale images, the shape shows both the number of images and each image's dimensions. Printing these values helps confirm the image size, channel depth, and dataset size being processed. This script shows how images can be represented with NumPy arrays. A small grayscale image is stored as a 2-dimensional array, then adjusted into red, green, and blue channels and combined into a 3-dimensional color image. It also creates a small batch by stacking 2 grayscale images. The printed shapes confirm the expected dimensions for the grayscale image, the color image, and the image batch. Sensor timetables. Sensor timetables organize measurements such as temperature or vibration by time, with each row representing a specific moment and each column holding a timestamp or sensor value. This turns raw data streams into structured data sets that are easier to analyze and use in AI projects. The order of rows matters because it shows the sequence of events, and that time context is essential for interpreting sensor readings correctly. In sensor time data, timestamps provide the key reference for understanding measurements in order. A well-structured timetable makes it easier to see what happened before an event, how quickly a signal changed, and whether sensors were aligned. Recording each measurement in its own column supports filtering by time, selecting sensors, and comparing patterns across periods, making the same format useful across many domains. When designing sensor timetables, it is important to define what each row represents. Data may be recorded at regular time intervals or only when events occur, and each pattern affects how the data should be analyzed. Because real datasets can include missing or duplicated records, clear time columns, measurement columns, and sampling patterns are essential for connecting the table to the real system and supporting reliable AI analysis. Python code, sensor timetables. Sensor tables organize engineering measurements that change over time. Each row records one moment, while the columns hold the time, sensor readings, and related labels. We begin by importing NumPy and pandas, 2 core libraries for working with data. NumPy supports efficient numerical array operations, while pandas helps organize and analyze tabular data. Together, they provide the foundation for managing sensor data and performing calculations on it. We create a regular sequence of time points with the pandas dateRange function, starting at 8 in the morning on January 1st, 2026. It includes 8 one-minute intervals, which is useful for organizing sensor data collected at consistent times. The data is organized into 3 parts: oven temperature readings in degrees Celsius, vibration speed measurements in millimeters per second, and mode labels for each reading. The labels divide the sensor data into 2 phases, with the first 4 readings marked as warm-up and the next 4 marked as steady state. We use a pandas data frame to organize sensor data into one table. It combines time, temperature, vibration, and mode labels so each reading is aligned with the correct moment. This makes the data easier to analyze and manipulate as a single, structured dataset. The sensor table is made easier to analyze by adding a minute column from each timestamp and a temperature change column that shows the difference between consecutive readings. When there is no earlier reading to compare, the change is set to 0. These additions make it easier to spot time-based patterns and temperature trends. We validate the sensor data by checking that the table contains the expected 8 rows and that the recorded times are in increasing order. These assertions help confirm the dataset is complete and properly ordered for time series analysis. The code announces that it will preview the sensor timetable, then displays the first 3 rows using a pandas data frame method. It formats the output without the index column, making the preview cleaner and easier to read. We summarize the sensor data by calculating 3 key features: the average temperature, the highest vibration level, and the fastest temperature increase between readings. Together, these values describe the typical temperature, the peak vibration, and the sharpest temperature rise during the recorded period. The code prints 3 key sensor summaries: the average temperature in Celsius, the highest vibration level in millimeters per second, and the fastest temperature increase per minute. Each value is rounded to 1 decimal place, making the results easy to read and useful for quickly assessing the sensor data. This plot shows sensor data over time using the pandas plot method. Time is placed on the horizontal axis, while temperature in Celsius and vibration in millimeters per second are shown on the vertical axis. Circle markers and a moderate plot size make the trends easier to see. The code formats the plot by giving it the title Small Sensor Timetable, labeling the horizontal axis as recorded time and the vertical axis as sensor value. It also turns on the grid, making the sensor data easier to read and compare against the axes. We use Matplotlib's plotting tools to create and display visualizations. The tight layout function improves spacing so plot elements do not overlap, and the show function makes the finished plot visible, especially in notebook environments like Colab. This script builds a short sensor timetable with pandas and NumPy, recording temperature and vibration once per minute over 8 minutes. It labels each reading as part of a warm-up or steady phase, adds simple time-based features, and calculates the temperature change per minute. The data is checked for the expected row count and correct time order, then summarized with key statistics such as average temperature, peak vibration, and fastest temperature rise. Finally, it plots both sensor readings over time to show the main trends. Time series features. Rolling statistics. Rolling statistics turn time series data into features that describe recent behavior using a moving window. Measures like rolling averages and rolling standard deviations can show trends such as warming or cooling, and reveal whether a signal is stable or variable. This gives models useful time-aware context, not just the current value. Window size in rolling statistics determines the timescale a feature captures. Short windows highlight quick spikes or drops, while longer windows reduce noise and show broader trends. Using several window lengths helps represent both fast fluctuations and slower patterns, in a form standard machine learning models can use. Rolling statistics help detect changes in condition or risk before they are obvious. They can reveal equipment drift, unstable production, or meaningful trends in patient vital signs more clearly than single measurements. To support reliable machine learning, these features must be built only from data available at the time of prediction, avoiding future data leakage. Python code. Rolling statistics. Rolling statistics describe recent sensor behavior by looking at values within a moving window. Smaller windows capture quick local changes, while larger windows reduce noise and make engineering signals smoother. We import 3 core Python libraries for data work: NumPy for numerical operations with arrays, pandas for handling and analyzing tabular data, and matplotlib pyplot for creating visualizations. Together, they provide the basic tools for data manipulation and visualization in Python. The process starts by setting a random seed so the results can be reproduced. It then creates a 1-minute timeline in seconds and adds a small linear trend, making the simulated vibration signal gradually increase over time. The synthetic vibration signal is built by combining a steady base value, a gradual trend, random noise, and a short spike. The noise represents normal sensor fluctuations, while the spike creates a sudden disturbance between 32 and 36 seconds. Together, these parts produce a signal that mimics real sensor data with both slow changes and abrupt events. We organize the generated data in a pandas data frame, with one column for time in seconds and another for vibration values. Then we check that it contains exactly 60 rows, confirming that the full 60 seconds of data is present and ready for analysis. We summarize the vibration signal with rolling statistics. A 5-second rolling mean smooths short-term noise and shows broader trends, while a 5-second rolling standard deviation shows how much the signal varies within each window. A 10-second rolling maximum captures the highest values, helping identify peaks or spikes. We narrow the data to the rows around the signal disturbance, focusing on time, vibration speed, and the 5-second rolling mean and standard deviation. This preview makes it easier to inspect how the rolling features behave during that period. The selected values are rounded to 3 decimal places and shown without row indices for a cleaner display. Create a clear plotting area. Then show the raw vibration signal over time to reveal the original sensor behavior. Add the 5-second rolling mean on the same plot to smooth short-term fluctuations and make the underlying trend easier to see. The plot is made easier to interpret by labeling the time axis in seconds and the vibration speed axis in millimeters per second. A clear title explains that the visualization highlights local signal behavior using rolling statistics, and a legend distinguishes the raw vibration data from the rolling mean. To finish the visualization, use matplotlib's tight layout function to clean up spacing and prevent plot elements from overlapping. Then display the plot so the rolling statistics and raw vibration data can be compared visually. This script creates a synthetic vibration signal with a trend, noise, and a short disturbance, then uses rolling statistics to analyze it. A 5-second rolling mean smooths the signal to reveal local trends, while the rolling standard deviation and 10-second rolling maximum help show changes around the disturbance. It prints a small preview of these results and plots the raw signal with the rolling mean to show how smoothing reduces short-term fluctuations. Peak features. Peak features summarize the most important highs or lows in a time series, such as sudden spikes or drops in sensor readings. They capture key details like the largest value, the number of major spikes, or when the biggest spike occurs. These features are useful when extreme events reveal more than average behavior, helping turn large datasets into compact signals for prediction and fault detection. Peak analysis means separating meaningful peaks from normal sensor noise. Small fluctuations in vibration or temperature may be expected, while a true peak should reflect an important change, such as abnormal vibration or a sustained unsafe temperature rise. Simple features can use maximum values or threshold counts, while more advanced ones consider peak duration and frequency. The key is to define peaks based on the physical meaning of the data and the purpose of the model. Peak features turn raw time series signals into clearer inputs for machine learning by summarizing important events through measures such as height, count, and duration. These features can make model predictions easier to understand, especially when detecting risks like pressure spikes in machinery. To be reliable, peak extraction should be paired with data cleaning and domain knowledge, since extreme values may come from sensor errors or irrelevant disturbances. Python code. Peak features. Peak features highlight important events in a signal and help connect those events to their physical meaning. This script demonstrates the idea using small examples based on synthetic vibration data. The script begins by importing 3 core libraries for data work. NumPy supports efficient numerical calculations. Pandas organizes signal data in tables, and matplotlib is used to plot the data for visual analysis of peaks and thresholds. Together, they provide the main tools for processing and visualizing the signal. The process begins by setting a random seed, so the generated results are reproducible. A time axis is then created with evenly spaced values from 0 to 10 seconds. Finally, a small 1 cycle per second sine wave is used as the base signal, providing a smooth periodic foundation for synthetic vibration data. Random noise is generated to represent measurement error using a normal distribution with mean 0 and a standard deviation of 0.06. This noise is the same length as the time axis, then added to the clean vibration signal to create a more realistic sensor-like signal. The final check confirms that every time point has a matching vibration value. To create visible peaks in a vibration signal, we choose specific positions in the signal and assign a boost amount to each one. These boost values are then added to the signal at those positions, increasing the amplitude only at those points. This simulates sudden vibration spikes that can occur in real-world data. We organize the sensor data in a pandas table with time in seconds and vibration in G for each measurement. A threshold of 0.75 G is then used to identify meaningful vibration peaks. By marking which readings exceed this threshold, we create a simple way to count and analyze peaks in the signal. The vibration data is summarized by finding its highest and lowest recorded values, counting how often it rises above a chosen threshold, and identifying when the strongest vibration occurs. Together, these measures show the signal's range, the number of significant peaks, and the time of the maximum peak. The vibration signal is summarized by first finding its median, which represents the typical signal level. The peak margin is then found by comparing the maximum value to this typical level, showing how strongly the largest peak stands out. These results, along with the signal's maximum, minimum, peak count above a threshold, and time of maximum value, are stored in a structured table for easier review and analysis. The code presents a concise summary of peak features in the vibration signal. It prints a clear heading, shows the rounded feature table without extra indexing, and reports the threshold used to identify peaks. Together, these outputs help the user interpret which signal features were treated as peaks and why. A new wide plot is created to show vibration data over time. The data points are marked with circles and connected by a line to reveal the signal trend. A dashed red horizontal line marks the peak threshold, making it easy to identify where the signal exceeds that level. The scatter function in matplotlib is used to mark vibration readings that exceed a threshold, highlighting them as red dots on the time series plot. These points are labeled as counted peaks in the legend, for clarity. The plot is then completed with axis labels for time in seconds and vibration acceleration in g, along with a title describing it as peak features from a sensor time series. Add a legend to identify key plot elements such as the threshold line and peak points, then adjust the layout so labels and titles do not overlap. Finally, display the plot to inspect the vibration signal and its peak features. The script creates synthetic vibration data by combining a sinusoidal signal with random noise and adding 3 clear peaks. It stores the data, then calculates key peak features such as the highest and lowest vibration values, how many peaks exceed a threshold when the largest peak occurs, and how strong it is relative to the median level. It prints these results in a compact table and plots the signal with the threshold and detected peaks highlighted to make the peak behavior easier to interpret. Trend features. Trend features describe the overall direction and rate of change in a time series, rather than focusing on individual data points. In engineering sensor data, they can show whether a signal is rising, falling, or staying stable, such as temperature increasing during operation or pressure dropping from a leak. This makes complex signals easier for machine learning models to use and easier for beginners to interpret. Signal trends can be captured by comparing values from the beginning and end of a recording, or by comparing averages across sections to reduce noise. These features show whether a signal is gradually rising or falling, changing suddenly, or staying stable. For example, voltage, vibration, or temperature patterns can indicate different system conditions, making trend features simple and useful to interpret. Trend features work best when they match the timescale and context of the data, such as rapid changes in machine recordings or slower shifts in environmental measurements. It is important to separate real trends from noise or regular cycles, like a pump turning on and off. When combined with rolling statistics and peak features, trend features help models understand typical levels, spikes, and overall direction, giving a clearer view of how a system changes over time. Python code trend features. Trend features capture the overall direction of a signal, helping summarize how sensor readings change over time. Small sensor examples build engineering intuition, while tools like NumPy and pandas make these features easier to compute and understand. We begin by importing 3 key libraries: NumPy for efficient numerical work, pandas for organizing and manipulating tabular data, and matplotlib pyplot for creating plots. Together, these tools support data handling, computation, and visual analysis of signal patterns. We create a time axis with NumPy's arrange function, producing 12 evenly spaced points from 0 through 11. An assert statement then checks that the array contains exactly 12 values, confirming the time axis is ready for analysis. Three simple vibration signals are created to show different trends over the same time period. One stays nearly stable with a small oscillation around a constant level. One rises steadily from a lower starting value, and one falls steadily from a higher starting value. Together, they illustrate stable, increasing, and decreasing signal behavior. We organize the vibration data in a pandas data frame with time in seconds and separate columns for stable, rising, and falling signals. This structured format makes the signals easier to manipulate, compare, and analyze, especially when applying trend analysis across them. The trend features function prepares data for trend analysis by converting both the input values and their time points into floating point arrays. This gives the data a consistent numerical format, making it ready for accurate trend extraction. The code validates the inputs before analysis by checking that the values and times are each one-dimensional, have matching lengths, and contain at least 4 data points. These checks ensure every value has a corresponding time and that there is enough data for trend analysis, helping catch formatting errors early. The code compares the signal's early and late behavior by averaging its first 3 values and its last 3 values. These 2 averages show the signal's starting level and ending level, helping reveal whether it changes over time and whether a trend is present. To measure how a signal changes over time, fit a straight line to the data using NumPy's polyfit function and use the first returned coefficient as the slope. This slope gives the signal's rate of change per second. The total change is found by comparing the final signal value with the initial value, showing the overall shift in amplitude from start to finish. This code returns a pandas series that summarizes key trend features of a signal. It includes the average near the beginning, the average near the end, the overall change from first to last value, and the slope per second from a simple line fit. Together, these values give a compact view of how the signal changes over time. First, the time column is removed, so the analysis focuses only on the vibration signals. A trend feature extraction function is then applied to each signal using the original time values. The results are transposed, so each signal appears as one row, making the extracted features easier to compare. A new direction column is added to the feature table to summarize each signal's trend from its slope per second. Using NumPy's where function, signals with slopes above 0.005 are marked as increasing, those below -0.005 as decreasing, and the rest as stable. This gives a simple, readable label for the overall trend of each signal. The output begins with a short message introducing the trend features extracted from the vibration signals. It then displays the feature table, with values rounded to 4 decimal places for readability. The table is converted to a printable string, so the results appear in a clear, organized format. Create a clear plot that compares 3 signals over time: stable, rising, and falling. Each signal is drawn on the same graph with circle markers and a label, making it easy to distinguish them and observe how their trends differ. The plot is made easier to interpret by labeling the time axis in seconds and the vibration amplitude axis in inches per second. A clear title explains that the trend features show overall direction, and a legend helps distinguish the different signals. Matplotlib adjusts the plot layout to make it easier to read, using the tight layout function to improve spacing around some plots. The show function then displays the plot, so you can visually compare the vibration signals and their trends. This script compares 3 vibration signals over 12 seconds, one stable, one rising, and one falling. It uses data analysis tools to calculate early and late averages, total change, and the slope of a linear trend for each signal. Based on the slope, each signal is classified as increasing, decreasing, or stable, and the results are summarized and plotted for easy comparison. Cross-modal models. Shared evaluation setup. Fair model comparison requires a shared evaluation setup, especially when models use different data types such as tables, images, or time series signals. If data preparation, labels, products, timeframes, or test splits differ, the results may reflect experimental differences rather than true model quality. Using the same prediction task in data splits keeps the comparison focused on the feature sets and modeling approaches themselves. For a shared evaluation, first define the exact unit being predicted, such as a part or inspection event. Then align every data source to that same unit, so each example represents the same real-world case across tabular, image, or time series data. Without this alignment, models may learn from irrelevant information and produce misleading performance comparisons. Fair model comparison requires the same rules for splitting data, pre-processing features, and reporting results. All models should be tested on the same unseen cases, while respecting factors like time and location to avoid biased results. Pre-processing must be learned only from training data to prevent leakage, and models should be judged with the same metrics so their performance can be compared reliably. Python code. Shared evaluation setup. Use one shared data split to compare modalities fairly. Keep the tiny synthetic inspection data easy to read, and use NumPy and pandas to manage all features. The script begins by importing 3 key Python libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas helps manage and analyze tabular data. And Matplotlib's plotting tools create visualizations. Together, these imports prepare the script for data manipulation, analysis, and visualization. To make the lecture results reproducible, the random number generator is seeded with 42, so the same random values appear each time. The dataset is then set to contain 80 parts, and each part is given a unique identifier from 0 through 79 using NumPy's range creation function. The data simulates 80 parts using 2 measurements, wear and heat. Wear values are randomly generated around 0.45 millimeters, while heat values are generated around 72 degrees. Each part is then labeled as defective or not by combining its wear value with its heat value divided by 200, and marking it defective when that combined score is greater than 0.86. A pandas data frame is created to organize part measurements in a table. It starts with wear and heat measurements, then adds a length column filled with random values from a normal distribution centered at 4 inches with a small standard deviation. This structured format makes the data easier to analyze and compare. We create simulated image grids for each part using random values centered around a baseline level. To model defects, we add an extra random component to the grids for parts marked as defective, so the image data reflects defect influence. We then summarize each grid by its average value and store these image means in a data table for later comparison with other features. A time axis with 30 points is used to build signals for each part. Each signal starts as small random noise, and a 4-cycle sinusoidal pattern is added only for parts marked as defective. The root mean square is then computed across time for each part, producing one overall signal magnitude value stored in a data frame for later analysis. The data indices are first randomly shuffled to create an unbiased split. The first 56 are used for training, and the rest are kept for testing. A final check confirms that the training and test sets do not overlap. A nearest centroid classifier predicts a test points class by comparing it to the average center of each class in the training data. It first finds the center for class 0 and class 1, then measures how far each test point is from those centers. Each test point is assigned to the class with the closest center. The evaluate function applies the same assessment process to each feature set. It converts the data to a numeric array, splits the features and defect labels into training and testing parts, then uses the centroid predict function to classify the test data.
It returns the feature set name and the accuracy, measured as the share of correct test predictions.
The evaluation compares tabular data, image features, and time features using the same evaluation function. For each modality, the function returns its name and accuracy, and these results are stored together.
This makes it easy to compare how well each data type performs under a consistent method.
The output first notes that all models are evaluated using the same target, data split, and metric, so their results are directly comparable. It then goes through each model result and prints the model name with its accuracy rounded to 2 decimal places. This creates a compact summary that makes model performance easy to compare. The results are summarized by taking each feature set name as a label, and its accuracy as the score. A bar chart is then created to compare these scores on a shared scale from 0 to 1, with the y-axis labeled as test accuracy. The chart highlights how the feature sets perform under the same evaluation setup. This script compares tabular, image-like, and time signal data using the same evaluation process. It creates synthetic data for 80 parts, including wear, heat, and defect information, then trains a nearest centroid classifier to predict defects. Each modality uses the same train test split and accuracy metric, ensuring a fair comparison. The final results report and visualize the accuracy of each feature set. Feature set comparison. Different feature sets offer different views of the same problem, such as tabular measurements, images, or time-based signals. Each can reveal or hide important information, so the data representation should match the physical process and the decision being made. Improving a model is not only about choosing an algorithm, but also about choosing the feature view that best supports the task. Different feature sets offer different views of the same prediction problem. In quality control, tabular data may capture defects tied to machine settings, while image or time series data can reveal visual damage or changing patterns over time. Comparing models shows whether a simple feature set already contains the key information, or whether richer data adds useful insight. When comparing feature sets, look beyond accuracy and consider storage, pre-processing, communication, and real-world reliability. Rich data such as hospital time series or drone images can improve predictions, but it may also introduce missing values, noise, or environmental variation. In some settings, simpler tabular data may be easier to maintain and explain. The key is to judge whether any performance gain is meaningful, stable, and practical to use. Python code, feature set comparison. This task compares different feature sets for a single inspection problem. It uses tiny synthetic data to keep execution fast and simple NumPy-based models to avoid extra library dependencies. The script begins by importing 3 core libraries for data work. NumPy supports efficient numerical operations and arrays. Pandas handles tabular data analysis, and Matplotlib creates graphs and charts for visualization. Together, they provide the main tools for processing and understanding data. We initialize a reproducible random number generator with a seed of 42, so the same random values are produced each time the code runs. We also set the dataset size to 90 data points, which determines the length of the synthetic data arrays. We model hidden defect severity as values drawn from a normal distribution centered at 0 with a standard deviation of 1. Then we add smaller normally distributed noise with a standard deviation of 0.35 to represent real-world variability and measurement error. 2 production measurements are created to reflect how defect severity may affect manufacturing outcomes. Feed rate in inches per minute increases from a base value as severity rises.
while thickness in millimeters decreases from its base value as severity rises. Both measurements include random noise to represent real-world variability. We create simple image-like features that increase with defect severity, while still including random variation. Bright spots start from a base level and rise with severity, with small, normally distributed noise added. Edge count is modeled the same way, but with a larger base value, a stronger severity effect, and more noise. Together, these features simulate both predictable and random changes in images as defects become more severe. To simulate real-world time series inspection data, we create signal features that vary with severity and random noise. The vibration peak starts from a base value of 1 and increases with severity, while the temperature slope starts from 0.2 and also rises with severity. Small, normally distributed noise is added to both features to make the simulated signals more realistic. Each part is labeled as defective by adding random noise to its severity value and checking whether the result is greater than 0.25. The true or false outcomes are then converted into ones and zeros, creating a defect label for every part. We use a pandas data frame to organize the generated features and defect labels into one structured table. It stores measurements such as feed rate, material thickness, image-based counts, vibration, and temperature trends, along with whether each part is defective. This makes the data easier to analyze and manage with pandas. The code first confirms that the dataset has the expected 90 rows and 7 columns, so each part includes all required features and its label. It then checks that the defective label uses only 0 or 1, representing non-defective or defective parts. These checks help catch dataset errors before further analysis. The features are organized into groups to compare different views of the data. Tabular features describe basic measurements such as feed rate and material thickness. Image style features capture visual patterns like bright spots and edges. And time series features describe changing signals such as vibration and temperature trends. A combined group includes all of these features, allowing us to test whether using every feature type improves prediction performance. We randomly shuffle the data indices, then split them into training and test groups. The first 60 shuffled indices are used for training, and the rest are held out for testing. This lets the model learn from one subset and be evaluated on unseen data. The function prepares data for a near-centroid classifier by splitting the selected features and labels into training and test sets. It uses the given indices to choose the appropriate rows, keeps only the specified feature columns, and converts the feature data into NumPy arrays for model training and evaluation. To standardize the data, first compute the mean and standard deviation of each feature using only the training set. Subtract the mean and divide by the standard deviation, with a tiny adjustment to avoid division by 0, so each feature is centered and scaled. Apply the same training set mean and standard deviation to the test data to keep the scaling consistent. To classify the test data, we first find a centroid for each class by averaging the training points labeled 0 and 1 separately. Then we measure how far each test point is from both centroids using Euclidean distance. Each point can be assigned to the class with the closer centroid. The code classifies each test point by checking which of two class centroids is closer. It assigns the point to the nearest centroid's class, producing a binary prediction. It then compares these predictions with the true labels and returns the accuracy as the proportion of correct results. We compare several feature sets by measuring how accurately a simple centroid-based classifier predicts inspection outcomes. Each accuracy score is stored by feature set, then converted into a sortable summary. Sorting the scores from highest to lowest makes it easy to see which feature representation performs best. The output introduces a comparison of feature sets using a simple classifier, then reports each feature set's accuracy. Each result is displayed with the feature set name and its accuracy rounded to 2 decimal places, making it easy to compare performance at a glance. This code creates a bar chart to compare test accuracy across different feature sets. It sets up the figure, plots each feature set with a distinct color, and labels the y-axis as test accuracy. The chart uses a suitable vertical range, a clear title, and a light y-axis grid before displaying the final visualization. This script creates synthetic inspection data with several feature representations, including tabular, image style, time series, and combined features. It splits the data into training and testing sets, standardizes the features, and evaluates each representation with a simple nearest centroid classifier. The output compares the accuracy of each feature set in a printed summary and a bar chart, making it easy to see which representation performs best. Model comparison. When comparing models built from tabular, image style, and time series data, the goal is to learn which representation gives the most useful insight, not just which model scores highest. A model should be judged by whether it captures meaningful patterns rather than random details. Well-designed tabular features may outperform a more complex image model if they reflect the key behavior, while image or time series data may reveal patterns that tables miss. The best choice is the data form that most clearly supports the decision being made. When comparing models, consider both the algorithm and the features it uses. Tabular data often works well with logistic regression or decision trees, while image data may need convolution-based models to preserve spatial patterns. Time series signals can often be summarized with features such as peaks and slopes, and then used in tabular models. Start with simple baselines before trying complex architectures, and use the best performing model to infer whether the problem is more time-related or spatial. When comparing models, look beyond accuracy and consider practical needs such as interpretability, data cost, and reliability. A slightly better model may not be the best choice if its data is hard to collect or its results are difficult to use. Good evaluation also includes error analysis, weighing the risk of missed critical defects against false alarms. In practice, performance metrics should guide decisions, not stand alone as final answers. Python code model comparison. Use simple engineered features to compare different modalities, keeping the synthetic data small so execution stays fast. Treat accuracy as just one clue for making decisions, not the only measure that matters. The script begins by importing 3 key Python libraries: NumPy for efficient numerical calculations, pandas for working with structured data, and matplotlib's plotting tools for creating visualizations. Together, these imports provide the basic tools needed for computation, data analysis, and plotting. A fixed random seed of 42 is used so the code produces the same results each time, which helps with teaching and debugging. The synthetic dataset is set to contain 90 data points, and a check ensures there are at least 30 so the analysis has enough data to be meaningful.
A synthetic defect dataset is created by first generating a hidden severity score for each part from a normal distribution centered at 0. Each part is then labeled as defective if its severity is greater than 0.25 and non-defective otherwise. This produces a consistent binary target array with one label for every part. The data creates 3 inspection measurements that increase with defect severity while adding random variation. Part age is based on a starting value of 24 months. Temperature starts around 70 degrees Celsius, and vibration starts around 0.12 inches per second, with each adjusted upward as severity rises. Random noise is added to each measure to make the simulated tabular data more realistic. We organize the generated tabular features in a pandas data frame with columns for age in months, temperature in Celsius, and vibration. This structure makes the data easier to manage, analyze, and use in later modeling or comparison tasks. We create a set of 8x8 image grids with baseline pixel values drawn from a normal distribution, centered near 0.25. Each image then receives a stronger central 4x4 region, where the added intensity reflects the defect severity scaled by 0.18. Finally, we check that the image array has the expected shape and contains the correct number of images. We create simulated vibration signals for 90 parts across 40 time points from 0 to 1. Each signal starts with small, normally distributed random noise, then receives a sinusoidal vibration pattern whose amplitude increases with defect severity. The sinusoid completes 6 cycles over the time span, modeling how more severe defects change the vibration response. The final signal matrix is checked to confirm it has 90 rows and 40 columns. We create a pandas data frame of simple image features for analysis or modeling. For each image, we record the average pixel intensity to represent overall brightness, the average intensity of a central patch to capture local variation, and the maximum intensity to identify the brightest point. We extract key features from time series vibration signals and store them in a pandas data frame for analysis or modeling. For each signal, we calculate its average value, its highest absolute peak, and its standard deviation to capture overall level, maximum intensity, and variability. The centroid accuracy function evaluates a simple nearest centroid classifier. It first converts the feature data to floating point numbers and the labels to integers, so they are ready for numerical classification. The data is then split using 70% for training and the remaining portion for testing to measure the model's accuracy. The data is split into training and testing portions using the same split point for both features and labels. This lets the model learn from one part of the data and be evaluated on a separate part. The code also confirms that the test set contains data, so accuracy can be measured. To normalize the data, we first find the mean and standard deviation of each feature in the training set, adding a tiny value to the standard deviation to avoid division by 0. The training data is then standardized by subtracting the mean and dividing by the standard deviation, which centers it around 0 with unit variance. The test data is normalized using the same training mean and standard deviation, so that training and testing remain consistent. The method represents each class by the mean of its standardized training samples, forming a centroid in feature space. For each standardized test sample, it computes the squared Euclidean distance to every centroid and assigns the class with the smallest distance. Accuracy is then measured by comparing these predicted classes with the true test labels. A pandas data frame is used to compare a nearest centroid classifier across 3 feature types: tabular data, image style features,
and time series features. For each feature set, the centroid accuracy function is applied with the same labels to compute accuracy. This creates a simple side-by-side comparison of how well the model performs on each kind of data. The code prints a header to introduce a comparison of the nearest centroid model across feature sets. It then converts the results table into a clean text display, hiding the index and rounding accuracy values to 2 decimal places. This makes the output concise and easy to compare. This creates a compact bar chart comparing test accuracy across different feature sets for the same simple model. The feature sets appear on the horizontal axis. Accuracy is shown on the vertical axis from 0 to 1, and each bar uses a distinct color for clarity. The chart is labeled, titled, neatly spaced, and then displayed to the user. This script creates synthetic machinery defect data in 3 forms: tabular measurements, image-like grids, and time series vibration signals. It trains the same nearest centroid classifier on each data type and compares how accurately each one predicts defect severity. The results are shown as accuracy scores and summarized in a bar chart, making it easy to compare the performance of the 3 data modalities.
In this lecture, you learn to represent simple inspection images and sensor time series using NumPy arrays and pandas tables, extract beginner-friendly features from image-style grids and temporal engineering signals, and compare model performance across tabular, image-style, and time series feature sets. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.